good afternoon. Let's start the presentation since I want to show you multiple demos, so and it's shorter than usual. So I am Tugdual Grall, or Tug. I'm working at Mapar. Mapar is providing a big data platform allowing you to stream, store data at scale, and I will use that during my demonstration. And as you can guess from my accent, I'm coming from France, and I don't speak Italian. And part of my job is to work with communities like today, building workshops or doing presentation, but also to meet a customer in a very early stage on a sales process. And this presentation comes from a pre-sales engagement we have done with one of the Formula One team. So it's not an Italian one. And their challenge is they wanted to build a new platform for their data. And it gave us the idea of building a demonstration, doing a slide deck that I'm presenting to you today. As far as I know, they have not the team has not yet built the new platform. They stay on their existing purely proprietary C and C# based solution. And the goal is about, for me, with Mapar being a platform focusing on data. How do we stream the data inside the system? How do you store? How do you query? How do you analyze the data? It's about what about the data in motorsport? And I will give you some ideas about the possible architectures and the different components you can use to build a real-time streaming platform that could be used in a racing team or any type of IoT device. And I have a small demonstration with different cars at the end also. So if you look at it, when you look in the paddock, you have many screens with engineers and drivers looking at them during the race, but after the race, during the engineering of the car. All these generate a lot of data that could be used in different ways. Some of the data will be used in real time. You have information about one car with the speed, the RPM, the engine speed, what are the Gs on the different side, left and right, and front and left, the gear positions, the wheels positions. All this is captured and streamed in real time to the paddock. And it allows the team to build different strategies when they want to choose when do they have to change or refuel the car. If they want, how do you want to brake on a specific curves? So they capture all this data to provide a strategy. We see here between different cars when comparing two cars or two strategies of the car different the race, and you see the blue car on the red one will be faster, one option to another. And we have to keep in mind that even if they capture a lot of data, they cannot configure the car live. They cannot change or they cannot ask the car to drive itself. Technically, it's possible, but they don't. What will be the point? And if you look at the data, it's interesting to see, and these numbers come from the discussion we had with the team or some of the numbers you can find on the internet. In a car, you have up to 300 sensors, and it was 2 years ago. So probably they have added even more sensors today. 2,000 channels will be communicating on the car, to the track, to the paddock, and it has to be as fast as possible to the paddock to give the information in real time. So they have their own network on a racetrack sending data. It's 1.5 billion data points for a race globally, 5 billion for the full weekend, and it's 5 to 6 gigabytes of data that are generated for 1.5 hours. And we got the number that in 2014, 243 terabytes of data was generated for the full weekend, from the Friday, Saturday, Sunday, for all the cars, for the race, the team, plus some information coming from the the race management, so like the weather, some temperature information, so global information that are not provided by the car itself. So the challenge now, it's really how do you do that? Where do you store? How do you store? And how do you use this data? And this is where the solutions that we push and the platforms that we build could help. It's not us, it's not Mapar or the data itself that will explain how to use the data to improve the drivers or improve the car. It's just the storing of the data, streaming the data in, do something with the data. So the way it works is, the way it works today is you have many things in the way the specific RF link, radio frequency link from the car to the global race organization that is then pushed into the paddocks on the engineering team. And this is what we see, for example, on the paddock, on the screen. So they stream the data, they have many screens. They can also do some analytics during the race and after the race. On some of the solutions, what we want to build and what we provided is to also push in real time to the factory. So this will be on the race track. This will be in the factory somewhere in the world. So like that, you can have an engineer starting to work on some data without having to wait until the race is done and the data are uploaded differently. So the demo that I have built to show how to build this kind of architecture of streaming data into the system obviously does not use a real racing car and doesn't have the volume because I want to be able to run that on my laptop or a single machine or even on a big cluster if you want. So it used something interesting that is a Torx project. Torx project is an open racing car simulator. It's an old racing car simulator project that has been used a lot in artificial intelligence on research platform because it's all the physics that you need if you want to simulate cars. It's from 2007, so it's quite old. You will see it from the graphics. But here's some interesting data. It's open source and provide a lot of information that could be used if you want to simulate things. So I show you the demo of the racing car, the demo of the racing cars, and I explain the architecture. Because the key part is, this is the way we want to improve the architecture of the car, of the platform for the Formula One team. So I have a very simple dashboard, empty for now. And I have my race car simulator. So Torx is, in this case, running in a VM in Linux. And I will just start a new race. This new race will start to generate data that will push into the platform. And you see the chart. So what we have here, we have the speed for each of the car, the RPM for each of the car by time. So depending of the racetrack, depending of the cars, you will see different speed. But what is interesting by distance, it's here. We will see each lap starting again. So you will see lap 1, lap 2, because it's very important for drivers and engineers to be able to compare how the cars are from one lap to another, and two cars in the same team to see how they react. Here I have all the cars. I didn't build any team. What is interesting on this, for example, is just you have the speed of the engine, the RPM, and the one that is very, very fast compared with the others. It's just because as part of the race car simulator, you have different type of cars. I don't know, Porsche kind of cars, and you have one that look like a Formula One or Indy cars. This is the one that it's at the top, as this one. And so what we see here, the RPM, the speed, the gear, the brake or the accelerator, the Gs, it's all the data that you can capture. And technically, you can even influence back. You can play with the video game. In my case, I just keep the stuff running. And data are stored into, are streamed in real time from this to the data platform. It's stored in the platform, but also pushed using WebSocket into this dashboard. And in addition to be visible in real time, it's stored inside the data platform on a data layer that can scale to the infinite, meaning you can create add many nodes. So you add more and you distribute data automatically, allowing the people to. My lap is too long. I should have selected a track that is shorter. I can use, for example, SQL to do some analytics on the data. Data are stored. I will give you a very first example of how data are stored in this case. I will zoom. So it's just gives the first 10 lines of the dots that have been generated, the ticks that have been generated, and they are stored into a database, a NoSQL database. And in my case, I use JSON as a format, just because it's easier to read. Okay, it's just not the best format for IoT, but at least it's simple for everybody to read. So we have, in this case, the race time and some dots that have been generated. And we will see the sensors, the distance, RPM speed, and that's it for now. And you can then do any analytics you want. And for example, in another query, I just use a standard SQL statement that will read the subdocument in JSON to create the average speeds by race for each of the cars. So we see for this specific race, this car, we have this average speed. The key point is, when we talk about big data, new data, IoT, and so on, a big part of the processing that is done, it's still done with SQL. You have a big part of the big data landscape is I want to be able to query data with SQL. And for many reasons. One is because everybody knows SQL. Not everybody necessarily as a developer or as an analyst, but as a tool. If you talk about SAS, about Click, about Tableau, everybody can talk SQL. So it's very often the first layer for analytics for data, including in very engineering-centric data. So it's one of the components that you want to be able to connect to this using JDBC or DBC to be able to do some analytics. And the architecture that I use for this is capturing data from the cars, streaming them into a data stream layer, and allowing different consumers. So we have even producer, even consumer. And this is a big change to the architecture we have provided and we offer to the team. It's to be able to completely disconnect the source from the target or for the consumer. In our case, we use MapperStream. MapperStream, it's an Apache Kafka implementation. And MapperDB JSON, it's a JSON database. But what is important from a developer point of view, you have the Kafka API, a standard open API, that will push data as they go, as a stream, into a queuing system, a messaging system, and you have multiple consumers. One in real time, the chart that I showed you. One will be saving data into the database, and I query them with another open source project that is a SQL engine on top of many data. And one of the challenges when we talk about data is when do you want to store them? And this is when you see 243 terabytes of data every weekend, you want to keep everything, if you want to keep everything. But I suppose in this case they want to keep everything. What will happen if you have different options to store the data? And in big data, we look at two parts. Databases, NoSQL or relational, and file system. And file system is a big part because it's a cheap, very reliable, easy to scale, easy to query way of storing the information. So usually you will use Hadoop file system or Mapper file system to store as many data as you want. It's very good if you want to store a lot of data, analyze a lot of data to do batch operation. or stream operation. But if you want to modify one single line, update some line, or do some lines, or deleting some lines, don't do that in a file system, don't do that in the database. So you have the choice of two. And usually you will have a mix of the both. In our case, for example, all ticks, if it's really 243 gigabytes, you will store that here on the file system. And you will have jobs on a stream base, on a real time or not, that will take this data either from the stream or from the file system to do some aggregation, some calculations that will be stored in the database. So keep in mind that you usually need two storage when you talk about large volume of data like they do for Formula One teams. The most important part about the new architectures, it's really about how do you want to capture the information. In my case, I didn't do any file copy. I didn't take a file, wait that this file is becoming big enough, and I copy it. I stream the data in real time from the sensor of the cars into the platform. So this is the data streaming part. And the data streaming part, it really will depend on what you want to deal with. It could be one event every hour, but it could be 11 million events every second, depending on what you capture. In the cars, it's a huge, huge part. But imagine if you start to talk about connected cars. Not talking about racing car in this time, but talking about a large volume of car generating a small volume of information. If a 100 million car, so if you look at a big brand, one of the big brands you have in the world, when the whole car will be connected, they will generate millions of messages every second. A car will not generate it a lot, but you will have many, many cars connected and generating data. So this is, you want to be able to stream the data at scale. And today, at least in the Apache, in the open source world, when we want to stream and we want to do something at scale, we use Apache Kafka. This is a very common library that has been used and built by LinkedIn in 2011. And the goal of Kafka at LinkedIn was to take data coming from many, many applications, many, many websites, be able to capture the information and process them independently. So really have streaming data inside the system and consume the data as you want, to do some analytics, to work on machine learning, really depending on what you want to do. And the model is a publish-subscribe model with producer and consumer. Very simple in terms of concept, very easy, and probably you are familiar with this in many of the messaging systems you have used already. The architecture doesn't change in this case, at least the global architecture. But Kafka has been built to scale, and the only way you can scale something where you have to store information is to partition. You have to divide in multiple partitions the data you have to deal with. And what happens when you build a topic into Kafka, you will say, I want X partitions. Like that, when you write, you will distribute the write in all the specific partitions. So you can say, I want 5 partitions. I have only 3 machines at the beginning. It will only work on these 3 machines. If you want to scale, you add 2 machines. It will distribute on the 5 machines. So you will be able to scale this way. And for the same reason, when you want to read, you will be able to create a set of consumer, what we call a consumer group for one application, allowing you to read in parallel on each of the partitions. So you want to be able to scale when you write. You want to be able to scale when you read. So this is a concept of partition for the storage of the messages. And consumer groups will read in parallel the different partitions. And Kafka will be careful or ensure that the order of the messages are the same in one partition. Between 2 partitions, you cannot guarantee the order. And this is important because if you start to have too many mechanics in the background to do transaction checkpoint between different messages or topics, you will have a hard time to scale. You want to make very simple operation, publish a message, store this message, replicate the message, it's done. On the other side, I want to read in parallel all the partitions. I just inform that I have read this partition in my consumer group. So when you deploy Kafka, you have multiple things to do. in terms of architecture on the server side, so you have multiple brokers, zookeeper to keep track of everything. And for this reason, Mapper build a different product. We use Mapper Streams. Mapper Streams is just the same, use the Kafka API, but have a different storage engine. We store that in our file system, so as soon as you have the cluster, it will scale as much as you want, with no management in terms of how do you partition physically the data, because it will be done by the cluster. But it's the same API. So when you produce a message, in this case, it's a simple Java example. You will say on which topic I am publishing. So if you are doing Kafka, don't be surprised by this part. This part is something that is specific to Mapper, is where do you address where the topic has to go. Since we don't have broker and you write into a multiple node cluster, you have to say what is my entry point, what is my namespace. In the context of Kafka, you are connected to one broker, so you don't need this. But it's the same, so usually when you move from Kafka to Mapper Stream, you just have this to change. You add a namespace or a stream, and then you publish and flush it to the message when you want to force the write on the network. Same for the read. Simple API. You just say, get the record from this topic. Every time you will have a message, you can consume it. And this, as soon as you need to write more, you just add new processes. As soon as you read and you need to read more, you add more consumer. It's very simple in terms of architecture. So one of the benefits of working with Kafka, of working with a platform that uses a file system or a NoSQL database, is you can easily create new services. You can easily create new API. You can consume new set of data. For example, in this first version, I only have this 3 sensor data. The first step will be to let's start to store more data. Coming, for example, use throttle and gears. And in this case, it will be just adding new element in JSON. Obviously, if you work in real life, you will probably work with a binary format that is a lot more efficient on the network than this. Protobuf, for example, would be a good example. But the key point is when we store this information, the engine that use the data, the drill engine, for example, what the SQL engine, the API that I build to build the web UI, it's not stuck on one schema. It's very important to think about the data in a way that you can add new elements over time. Because you want to keep data for 10 years. 10 years ago, I don't know that much about mechanics, but 10 years ago, I think they didn't have this electric power engine where you can accumulate energy in the Formula One, push a button and get some info. They want to capture this information now. So one of the components that we push in the architecture is use a streaming technology that has no schema or has flexible schema. Same for the storage, allowing you to store new element easily that you can consume. And one of the basic rules is don't delete attributes. Just add new attributes. In this case, it's very easy to change the new way of working with the data. And the key element about this architecture being streaming-based, when you stream the data in and you consume, it's very easy to add new services. And this is one of the, for me, this is the most important part. If you start to really think the data, I send a message that is a business event or a technical event that I can understand from a business point of view, it's very easy to add new services. To add a new consumer that will do instead of doing the streaming only, we'll do some processing, because here I have no processing. I just print the data on the screen. Here I just save the data in the database, and the processing is done by somebody else. And here I will use some stream processing for machine learning, aggregations, and so on. On the two technologies that we see, it's Apache Spark and Apache Flink. They have two of the big components that we see in a big data landscape around this. So this one is the most commonly used. And the key part, it has been built to do all the MapReduce, all the big, complex distributed calculation on aggregation you want to do on a large volume of data on many nodes in a faster way than before. Real time will depend, obviously, of the type of data you have, but what it can do, it can get the data directly from a stream. So you can pull the message directly out of a Kafka topic and do the calculation, do the processing. Same with Apache Flink. It's just different way of working. The big difference in the way they work, the framework, is Flink has been built first talking about streaming as a data flow. They want to stream data, they want to deal with the data in real time. Then over time, they added the batch-oriented processing, machine learning, and so on, where Spark started with a pure batch-oriented for large data set, and they added the streaming part. In terms of adoption on the market, Spark is far away. Far ahead, sorry. So I just want to show you here how you can easily add a new service once you have the topics and when you start to have data, any type of data you want. And suppose I want to calculate in real time the average speed of the car, or in this case, every 5 or 10 seconds. The only thing I have to do is to add a new consumer that will consume the data for this specific topic. The same data for a different use case now. So in this case, what I have is I use Flink, and I just get the data out of the topic. And then I create the operation to group by car. Every 10 seconds, give me the average speed. And the average speed is quite simple, will be get the car info, every time count the number of cars, the number of ticks you had, calculate the average speed. It's very simple stuff. So I'm starting the process, and in the same time I will start a new race. It uses the last message from the queue. And now you will see the speed for each of the car every 10 seconds. I didn't do any smart stuff here, but the idea is just to see now I have data coming in my dashboard. Data coming in the dashboard, continue to be saved inside the database, and just be saved, print, in this case, with the stream processing layer. So the key part on what we wanted to show in this case is you can easily ask your engineer to build new models to analyze the data in real time. And you can test that even in production. I don't change the data, I just consume the data. And one of the key elements also, all the events that you push into Kafka or mapper streams, you can keep them. So I have the history of all the race. Obviously, it takes some space on disk, right? But I can replay the race if I want from a pure analytics point of view. To replay this, to analyze when it was, for example, between two curves, what was the average speed between one point on the curves and the another in the curves. So when we discuss with the team, it's really providing a platform to store a lot of data. So you need a distributed file system on a distributed database. If you don't do that, you will have to manually do it yourself. So start to use partitions in relational database, and it could be very expensive and complex. In this case, the platform just do it. You start with 5 nodes, you add 5 nodes, and so on and so on. And also, using the streaming approach, you will decouple the source from the target, from the application that consumes the data. This one, let's say it's more or less for everybody that deal with big data. This one is for everybody. When you start to do microservices, it's what you do also. You decouple two different services, and you find a way to make them communicate. This one is very important for any developer, any architect today. But the key part of this, it's true for Formula One, They need this kind of new architecture to stream the data, process the data, and keep more data than before. But it's true for many, many industries. I can replace that everything by telcos. You want to be able to dynamically adjust the bandwidth to your key customer on your cheap customer. You keep the bandwidth for people that have a very expensive subscriptions, and you raise. It's what they are doing today, but they are doing it in a non-very smart way. You can start to add artificial intelligence and machine learning to do it. Fraud detection in finance and retail, this is a very common use case where you have exactly this architecture coming inside the system all the time. So it's really easy to apply this streaming-based architecture to any use case today, any type of industry today. And I have a small, so I'm working on a different demo, not Formula One, but this is this small cars. Who have played with this before? This is the best technology if you want to do machine learning and have hackathon. So I will put them on the floor. And it's exactly the same demo, except of using a software. I want to use a physical machine. So what I have is I have a small script that I have to find that I use an HTTP Node.js, a REST API developed in Node.js to connect to the car and put the car in motion, okay? And the goal is to stream the data from the car to my laptop, to the platform, to a dashboard. It's long. So just have to find. So they should change color. If not, okay, 1, 2, not yet, 2. And they should start to move. So what happened here now is they send data back to my laptop using Bluetooth. And here we go, the demo doesn't work. So let me just restart 2 services and see if it's coming from there, and I will. No, it's not. It's all the communication between. So let me explain then what happened and why it's quite nice to use. The way it works is the cars are using Bluetooth to communicate, and obviously this is not for. Usually it's a game you play on your phone. Okay, it's a mix of real cars and video games. Using Node.js, I push that on Mapper streams. And I consume using Vertex. You know Vertex? It's a very nice web streaming, or not web, development framework to build any type of application. The big benefits for this it's very easy to do WebSocket from this to push data in. And what is interesting, why it's interesting for hackathon, you don't have any intelligence in the car besides the fact that they follow the track and they know where they are on the track. And they send data. Okay, I may know why it's not working. Let me just do one test here. And they send data every time they move, and then you can program them in your lab. For example, this is what I put here. You can receive the message of all the cars, know where they are, and you can re-push the data back. So for example, you can ask to slow down, change the track, do a U-turn, on this kind of thing. And when I was looking to build this demonstration, I discovered that a company that is working on self-driving car, autonomous car, is using that as to explain. And it's quite fun. So the name of the product is this. So if you have boys, it's good. You can explain. You can say, it's what I said to my wife. It's for my kids. But so if you have any questions, I will stop them. No questions? Okay. Thank you.